So our final speaker today is Ben Castle, who's a postdoc at the Fields Institute. His talk is Strongly Minimal Expansions of Groups Interpretable in ACF0.
Okay, thank you. And thanks for the organizers for inviting me. So this is Strongly Minimal Expansions of Groups Interpretable in ACF0. And really what this is it's a partial case of a conjecture of Zilber. So I'm going to start by stating that. So this is called Zilber's restricted trichotomy conjecture. I'm sure most people here know of Zilber's original trichotomy conjecture, which just said that strongly minimal sets should either be locally modular or should interpret algebraically closed fields. And restricted trichotomy conjecture says exactly the same thing, but assuming that your strongly minimal structure is originally interpretable from the field itself. So if we have an algebraically closed field and a strongly minimal structure interpreted in that field, then one of two things should happen. Either your structure is locally modular or it should interpret the original field. Okay, that's subtly different than just stating that trichotomy is true of M, but it's equivalent because you couldn't interpret any other field than K in the first place. And okay, something to say about this to sort of clarify what we're doing is when we say interpreted structure, that's kind of saying you can forget some of the original data from the structure K. And so normally when you're trying to prove the trichotomy of some strongly minimal set in a setting where it's worked, you use geometric information to build the field. And the problem here is what could have happened is that we just forgot the geometric information when we built the structure M. So somehow the challenge is sort of without knowing what you dropped from K to go to M, you somehow have to like recover the topology from K. Okay, and again, it's equivalent to just saying the trichotomy for this all structures, strongly minimal structures, M interpreted in algebraically closed fields. And it's a statement that partial cases have already seen some nice applications. There's a really nice paper of Zilber called A Curve and its Abstract Jacobian, which solved a problem using a partial case of this. Okay, now, so this is an old, well, relatively old a problem, and so it would be far too difficult to list all of the papers on this problem, but just to give probably a couple of the most notable, Rabinovich, 1993, did the case when the structure M is just literally a reduct, not just an interpreted structure, but a reduct. So that means the universe is equal to the field. And prove that you can define the field. And so more generally, a very recent paper of Hassan and Sustertov handles the case when the universe is a curve. So we generalize from just the field itself to any one-dimensional set or equivalently any curve. But there we go. Okay, I have one more thing. So what's still the case that the universe is of dimension at least 2. And this is a little confusing, of course, because M is a strongly minimal structure, and strongly minimal structures you think of as being one-dimensional. And I'm saying that it's dimension 2, and so there's 2-dimension functions, one coming from the strongly minimal structure M and one coming from the field K. And so we're saying M is itself internally strongly minimal, but its universe happens to be a set of dimension at least 2 over K. And so to avoid confusion there, I'll generally use the word dimension to mean field dimension and rank to mean Morley rank in this strongly minimal structure M. Okay, so just to play around with this a little bit to get used to this, like there's 2 different structures here. I'm just going to state a couple easy facts. So first, if you have any set which is interpretable from M, then its dimension is its rank, but scaled by the dimension of the universe. So what this is saying is if the universe is like 3-dimensional, then the dimension of any definable set, or really any interpretable set, as computed from the field, is going to be 3 times as big as if it was just computed from M. And okay, just proof sketch. So it suffices to reduce to the case that T is just n to the R. So strongly minimal structures, after adding parameters, they sort of kind of partially eliminate imaginary. So any interpretable set can be put in finite to finite correspondence with a definable set, which can in turn be put in finite to finite correspondence with the power of the universe. And so finite to finite correspondences don't affect any notion of dimension. And so you can just reduce to the case of the power of the universe. And then it's fairly clear because the m to the r is just going to multiply everything by r, which is exactly what we're doing. Okay. So that's a easy exercise. And a corollary of this, which is relevant to the statement of the conjecture, is that no matter what, locally modular or not, if the dimension of m is at least 2, then you can't interpret the field. And so why? Well, assume that you can interpret an infinite field f, then looking at the equality I just stated, the dimension of f is at least the dimension of m. That's because it's a multiple of the dimension of m and it's positive because it's infinite. However, so f is interpreted in m, which is also interpreted in k. So f is interpreted in the field k. And well, it's a fact of Poisson that an infinite field interpreted from an algebraically closed field is actually just that same algebraically closed field. So f is necessarily definably isomorphic to the original k. And that means that they have the same dimensions. The dimension of f is the dimension of k, which is 1, and that's a contradiction. Okay, so this is nothing new. I'm just sort of playing around with this. And really the point is this. So if the dimension of m is at least 2, then the conjecture is just equivalent to local modularity. So we're not really saying if it's not locally modular, you can build a field. We're just saying it really should just be locally modular. Okay, historically, the way this has worked is kind of a two-part argument. And that's really kind of oversimplifying it, but kind of true. So what you do is you first assume non-local modularity, and I'll talk a little bit about what that means soon. But you assume non-local modularity and you build a group. And then once you have a group, you sort of repeat what you just did, but with better accuracy and build a field. So it's this two distinct steps where you build a group and then you build a field. And okay, well, this is a guess. I'm not claiming this, but you might imagine that you could do the same thing in this higher dimensional case, but it would look a little bit different. So the first step would be interpret a group. And the second step would just show that groups are locally modular. And so that's what I'm going to do. So this talk is precisely that. So groups are locally modular in characteristic 0. Now, you might say, okay, what about characteristic P? And what I can say is there are definitely, I think, parts of this argument that would be not much of an issue in characteristic P. But a decent portion of the argument is going to use the Euclidean topology on numbers. In particular, it's going to use omnimality, which is really inaccessible in characteristic P. So for now, this is just a characteristic 0 statement, although I expect characteristic P would also be doable. So statement of the result. This is one of the results from my thesis. So if you have an algebraically closed field of characteristic 0, and M is a strongly minimal expansion of a group, M plus, which is interpreted in K, and the universe of M is dimension at least 2 according to K, then M is locally modular. Because this is precisely the original statement, but just in characteristic 0 and assuming you have a group operation. And notice if you combine with the result of Hassan and Sustertov, so the Hassan-Sustertov result is just the entire conjecture in dimension 1, so for curves. And so if you have the entire conjecture for curves and you have the group part for bigger than curves, then what you have in particular is the group part for everything. So this implies the restricted trichotomy conjecture for strongly minimal expansions of groups in characteristic 0. Okay, now at some point I think most of you are familiar with this, but I should really talk a little bit about what local modularity is. So the intuition is that in the original trichotomy principle of Hilbert is that strongly minimal structures kind of come in two really distinct sort of rungs or levels. There's the complicated ones and there's the simple ones. So we have a dividing line and we just call it local modularity. The simple ones are locally modular. The complicated ones are not locally modular. And okay, the nicest way to see it is probably using these things called plane curves. So a plane curve in M is a subset of the plane, which is M squared. So you kind of use that intuition that M squared is the plane. So a subset of M squared of Morley rank 1. And so note, I'm talking about Morley rank, I'm not talking about K dimension. So this is kind of confusing because a plane curve is not actually a curve, it's something bigger. But it's a plane curve if M is what's deciding it's a plane curve, if that makes any sense. So anytime I say plane curve, I'm talking about rank 1 set according to the structure M, which means it's actually bigger than that. Okay, and a stabilizer of a plane curve is basically the stabilizer of the generic type. You can't quite say that because there might be more than one generic type. So it's the group of elements that you can shift C by so that the result is almost equal to C, so that they have finite symmetric difference. Okay. And this is always a definable group over the same parameters that would define C. Okay, now the main thing that lets you talk about local modularity is this notion of an almost faithful family of plane curves. Now, really what you need is a faithful family of plane curves to define local modularity this way, but there are benefits to this notion of almost faithful in comparison to faithful. And I didn't really have to say it, but to sort of respect the fact that it's what's actually used, I'm going to say almost faithful. So an almost faithful family of plane curves of rank R is a definable family of these things. So we have F inside M squared times A is the parameter set such that each of these fibers F sub A is a plane curve. And almost faithful is this condition 3, which says, this is kind of supposed to say that any two of these are not the same. So any two of these have finite intersection. But the almost part kind of messes with that. So the actual definition that's used generally is that each one has infinite intersection with only finitely many others. Okay, and if you want to know why do we care about that, why don't you just say faithful? It has to do with the fact that you can eliminate the almost equality relation kind of up to finite error. So the point is that the parameter set can be a definable set, not an interpretable set, if you are willing to relax faithful to almost faithful. If you don't know what I'm talking about, don't worry about it. So, and then the rank of the family is the Morley rank of the parameter set. Because that's a family of curves. Just think of it as a normal, just a family of sets, and the rank R is like the dimension of the family. Okay, so not locally modular has the following equivalent conditions. So, one, there exists an almost faithful family of plane curves of rank at least 2. So locally modular would mean you only have rank 1 families. It's kind of saying like there's only the linear level. And you think of rank at least 2 as being like higher degree. 2, there are almost faithful families of arbitrarily large rank. So it's a fact that once you get a rank 2 family, you can grow it to rank anything you want. And then in the specific case of groups, and at least in the specific case of the groups I'm talking about, which are interpreted in ACF0, it's equivalent to having a plane curve with finite stabilizer. And I need to say Morley degree 1 for that to be a true statement. So a stationary plane curve with finite stabilizer. And then if you want, you could even make the stabilizer trivial, but you might have to change the group. So if you have finite stabilizer, then you kind of mod out by the stabilizer. There's a way to do that. And so that you can interpret a strongly minimal group so that in the result, you have trivial stabilizer. Okay, so there's 2 ways of thinking it. There's families of plane curves get really big. That's not locally modular, or equivalently, you have plane curves with trivial or finite stabilizer. Okay, and so my goal is to prove local modularity, assuming this dimension of the universe is at least 2. So what does the outline look like? So I'm not going to say much at all about this point 1, but it's just like straightforward standard reductions reduced to a nicer situation. So you have a group definable from an algebraically closed field. It's known that all of those are algebraic groups. You have a strong minimal group, and it's known that all of those are commutative. And well, it's not so hard to see that irreducibility can be seen using the group operation only. So you can detect irreducibility, and then because strongly minimal things have degree 1, you get irreducibility, so et cetera. So you just tweak the situation a little bit, and you get an irreducible commutative algebraic group. And you do that thing that I said where you can sort of mod out by a stabilizer. Here on this slide, so you can mod out by a stabilizer, and you end up with a plane curve which has trivial stabilizer. So that's my list of initial assumptions, is irreducible commutative algebraic group, and there's some plane curve with trivial stabilizer. Okay, once you have all this, you have all the machinery that comes with algebraic groups. So we know that M is. Sorry, is there a question?
Yes, Ben. So can you just, what are you proving?
This theorem. So I have an algebraically closed field of characteristic 0, K. I have M, which is strongly minimal and interpreted in K, and it's a group. So it contains a group operation. And I know the universe is at least 2, and I'm going to prove that it's locally modular.
Okay, and you're going to prove which one of the equivalent.
Oh, I see. It's which one is.
Yeah.
The conclusion is going to be that every Morley degree 1 plane curve has infinite stabilizer. So it'll be 3, item 3, if that's what you're asking.
Yeah.
Okay. Okay, so if I have an algebraic group, I know it's smooth. It's a variety, it's a smooth variety, and then I can view all the definable sets as constructible subsets of powers of that. So I'm viewing definable sets using the smooth variety structure of M. So the main thing that we have to do, the hard part, and really the vast majority of the proof, is this number 2, which is to show that not only does M have this nice structure, but so do basically all the definable sets. So what I want to do is show that definable sets in the structure M are geometrically nice when viewed using the topology on M. And what that means is up to finitely many points, each plane curve is going to be pure dimensional and closed. Okay, so that means that each plane curve is going to be a pure dimensional set with finitely many holes and finitely many isolated points. And once you have that, it's much easier. So the main step is an analysis of the geometric structure of what the definable sets could possibly look like. And then lastly, it's maybe a little bit easier to show that such sets have infinite stabilizer. And that'll get local modularity. And I should note that the vast majority of this is this item 2, which is to analyze the geometric structure of definable plane curves. I'm really following an outline given by previous authors, and it would be wrong to not credit them. So this was done in similar types of problems by papers of Hassan Kowalski, and then another paper from, so there are 3 authors. So that recent paper from, I believe, 2018, which analyzed strongly minimal groups, definable and minimal theories, but under more restricted settings. My result is not a corollary of theirs. So, okay. So what do? I'm going to go through a series of facts, and each fact is going to say plane curves look nice in the following way. Okay, and at the very end, you combine all those and have this nice structure result. So the first one is plane curves have finite frontier. And what do I mean by frontier? So the frontier of C is the closure of C relative to M squared minus C. So that's what I mean by frontier. This is an argument that goes back quite a ways. Basically, the technique of how do you try to definably recognize the frontier, if that makes sense, of a definable set without mentioning topology. And there's a way to do that, which is the following. So you take a frontier point of a plane curve. So you imagine a hole in the middle of a plane curve, and you want to try to sort of definably recognize where that hole is without mentioning any topology. So the first thing is you have to tweak the situation a little bit and try to make this a very generic instance of the situation. So you have a very large family of curves and a very generic member of that family of curves, and then a very generic point, which happens to be on the frontier. So you kind of make the situation look very, very generic, which is kind of a standard reduction. And then there's this formula, which, okay, that as written is not a first order formula, but can be made into a first order formula. And what it's going to say is plane curves containing the frontier point intersect the original curve less often than you would think that they would. And I'm gonna draw a picture of that in a second. So there's a way that's been used before for doing this. And what I basically did is I basically just gave you the formula. However, verifying that it actually works is quite complicated. So this is a fairly long proof of the fact that if this fairly simple formula actually correctly singles out the frontier point. But what we get from this is that our randomly chosen frontier point of C is actually algebraic over the parameters defining C. And that means that there are only finitely many. So here's my picture. C is this red set. You have a plane curve. And these blue sets are, I'm imagining, as a family of curves, which are just some other random family. And then in the middle of C, I drew a hole at x0. And I'm trying to recognize the fact that x0 is a hole of C, definably. And so what do? Is I say, well, most of these blue sets meet C twice, but the one that goes through x0 only meets C once. Okay, and so the definition of x0 is roughly, it's an element of the blue set that only touches the red set once. Okay, that's kind of how I'm singling it up. And again, that the idea for doing that is not original, but there's some things to check that would work. Now, the main step in this argument is the following, which is actually surprisingly difficult. So normally this is just done for plane curves, recognizing frontiers of plane curves, and the main step that makes this entire thing work is recognizing frontiers of rank 2 sets, which is surprisingly kind of a lot harder. But uses the same argument. So I'm going to define the rank 2 sets I'm talking about. So a non-trivial 2 hypersurface is just a subset of 3 space which has rank 2. So like a hypersurface in 3 space. But it's non-trivial. And what I mean by non-trivial is it's not just like a product of something in 2 variables with something in 1 variable. So each projection to 2 coordinates should be mostly finite to 1. And if you want a formal definition, you can think of it as if you take any generic point of D, what you get is 3 separately generic coordinates such that any 2 are independent, but any 1 is algebraic over the other 2, which we traditionally call a non-trivial configuration. And so here's really the main technical facts that's in this whole thing is you can, if you start with one of these sets, these non-trivial 2 hypersurfaces, you can contain its closure in another one. So if you go from D to adding all of the frontier points, all those frontier points are contained in a single other non-trivial 2 hypersurface, E prime, and that is defined over the same parameters, which is, I'm going to just say it's the same argument, but it's actually quite difficult. And what you have to do is arrange a family of rank 1 sets to intersect with D, which are going to have the same picture that I drew on the last slide. And in arranging that, it seems to be hard, but it works. I see I'm really kind of essentially out of time. So let me just mention the last sort of geometric fact is to deal with poles. So there's a definition of a pole, and it's exactly, capturing the definition you'd think of just something shooting off to infinity at an asymptote. And well, proposition, every plane curve has only finitely many of these. And I'll just draw a picture. And it's kind of nice because I don't have to define a whole bunch because the proof is to use Petersel-Steinhorn subgroups, which Will just talked about. So here's the picture. So I have this blue plane curve with a pole. And what I'm going to observe is that if I take two x values approaching my asymptote x0, so say x1 and x2 approaching x0, and I look at the corresponding y values, y1 and y2, I can arrange such y1 and y2 to have basically any difference I want, as long as that difference is somewhere vertical, right? And this is the observation of Petersville and Steinhorn, is that there's going to be an infinite set of sort of limit differences as my x's go to the pole. Well, a fact that was kind of observed in the past is that you can code all that information into a definable set, which happens to be a non-trivial 2 hypersurface. The set T here. And the neat thing that happens is that if you have a pole, then you get a whole bunch of elements of T bar, which have 2 coordinates equal, because it's like the 2x values approach the same asymptote. Well, what's going to happen then is that T bar has a whole bunch of points. If you have infinitely many poles, T bar has a whole bunch of points with 2 equal coordinates. And what that's going to violate is the non-triviality condition. It kind of gets a contradiction in an unexpected way, but it works. And so you get finitely many poles. Now, let me just say it's a straightforward observation, which has been observed by people in the past. This is essentially directly copied from a previous paper. If every plane curve has finite frontier and finitely many poles, it's possible to see that every plane curve is pure dimensional outside a finite set. And there's a picture of that, but I'm not going to talk about it. Okay, so every plane curve is pure dimensional outside a finite set. What do you do with that? Well, you take a plane curve and you define this other set in terms of the plane curve, which is going to be a fiber product which tracks intersections of translates of the plane curve. And this fiber product turns out to be also pure dimensional because the original one was. So we're going to measure intersections of translates of C. And I know I'm out of time, so what I'm going to say is that we just project this set R and observe that R very easily violates a standard algebraic geometry fact, the purity of ramification locus, except in one condition, which is that R is not a generically finite to 1 projection. So R does not project generically finite to 1. And what does it mean if this projection is not generically finite to 1? It means that most of the intersections of translates of C are actually infinite intersections. So somehow we get an easy contradiction to purity of the ramification locus unless you have a bunch of infinite fibers, so a bunch of infinite intersections of translates of C, and that pretty literally translates to C has infinite stabilizer. And okay, I am definitely out of time, so I will stop there.
Thank you. Please join me in thanking Ben for this great talk.